Hello.
Yeah, the next speaker is going to be Brooks Page, and he's going to talk about the grammar variational autoencoder.
Awesome. Hi, I'm Brooks. I'm a research fellow at Alan Turing Institute, and this is the grammar variational autoencoder, and these are Matt and Miguel, who are my co-authors on this, and I highly recommend them as collaborators. By the way, they're excellent. So I'm going to throw back slightly to maybe the first two talks from today. And so as motivation, we're going to think about optimization or inference in kind of complicated discrete spaces, and particularly thinking about optimizing molecules. So if you think about if you take a molecule, there exists chemoinformatics software which you can use to take the molecule as input and gives you properties of the molecule out. And so that's great, but what if you want to do the inverse problem and say, given that I would like to design a molecule that has some particular chemical properties, how do you get back and say, well, here's the molecule I should have? And in practice, people do things like take giant databases of like hundreds of thousands of drug-like molecules and just go and evaluate this on a bunch of them, or starting from a molecule that looks kind of good, you say, well, what sort of local changes can I propose to this molecule? What you don't have is any way of kind of, given that it's a discrete space, doing anything like taking a gradient backwards from the property through the chemoinformatics software to your molecule itself and say, well, this is how we should modify the molecule to change this property. So one thing which for me was surprising, my background's not in chemistry, is molecules. So here's the molecules on the left, and then on the right, this is text in the SMILES language. And this is basically source code for a molecule. And this is, I think, common for a lot of the discrete domains that we are sort of looking at, is there's this complicated structure, but there's also some nice kind of text representation that people use and is out there. So we're going to be looking at the SMILES language for molecules. But once we have our molecules as text, then so something which has been observed is people have worked a lot on generative models for text. And so in particular, we're going to look here at this variational autoencoder model for text based off of Bowman et al. And the way this works is I'm going to start in the middle, and we have this continuous latent space. Continuous latent space. And so you say, well, I'm going to define a generative model for text, and it starts with some point z, which is real valued, and we can go through this decoder through the right, which is something like a recurrent neural network, and this will give us probabilities of characters. And so you can sample out text given a single real valued vector. And then if you put it back in at the beginning at the input, or you put data as an input, there's a second conditional distribution Q of z given text, which will map an input into this latent space. And it spits out parameters mu and sigma that define a distribution over these real valued vectors. And the input here is just individual characters. So there's no real language model involved, or no explicit language model involved for this. You just encode here are the characters, and I'm going to run a sequence model over it. And so in addition to generating sentences, this lets you do all sorts of fun things. So in this paper, they do things like say, well, how do you interpolate between two sentences? One way you can do it is you say, well, I'm going to map two sentences into the latent space and then do linear interpolation in the latent space. So here they say, if we start from I want to talk to you and end with she didn't want to be with him, it proposes kind of a string of plausible intermediate sentences. And so this sort of suggests there's something like local structure here in this discrete space of text, which is being encoded well in the continuous latent space. So this was used in a recent paper of Gomez-Bombarelli et al. For molecular synthesis. And so here we say, well, our text is SMILE strings, and we're going to say, so here, we have Q of Z given molecule and P of molecule given Z are the models we're learning. And this lets you generate a model from the latent space just by kind of using best practices from neural language models. So you take in a sequence input, a sequence of characters, and it goes into the latent space. And now you can say, once you fit this model, you can say, well, I know that I can take my sequence input over here and put it into the chemoinformatics software and get out properties of the molecule. But that may be expensive to run. I don't know how to then optimize. What if over here I say, take my Z in this continuous latent space and fit some sort of predictor through to predict from the latent space, from these learned features, the property that we might care about. And so then now you have something which is hopefully a smooth space. You can maybe take gradients backwards through your predictor and so on. So this hopefully simplifies this optimization problem. And so one thing which is kind of magical here is this is unsupervised. So this continuous embedding is learned kind of regardless of what property you're ultimately trying to estimate. This really just looks at the smile string and then gives you a latent space, and these turn out to be good features. So this is super successful. But this is, I put text in quotes here because this isn't really like natural language. Smiles is a specialized language, and this has some challenges and some advantages. So if you take a smile string here, it's very strict. So if we're kind of sort of robust to things being a little long in English text, and we're like, yeah, I know what it means, but if you change this just won't parse. So single character errors give you strings which are not even in this formal language. But on the other hand, it's awesome. Like Smiles is a formal language. It's context-free. There's a context-free grammar. It's sitting there. We know it. Parses are unique. There's a dynamic programming algorithm. Given a string, we'll just hand you a parse tree. So it would be nice to kind of use this somehow. And so that's what we do to try to basically improve on the quality of the embeddings that we get out. And so the basic idea is instead of generating smile strings character by character, we generate them by using the production rules in the grammar to build it up via a parse tree. So I'm going to walk through this step by step. So first, encoding. So we're going to get a distribution over a Z given a molecule. So here's benzene down in the bottom right. And here's a subset of the grammar for Smiles. So this is just a few of the rules that we need for benzene. And so if you're not familiar with the context-free grammars, here we have, these are all production rules. This is a table of production rules that we have around. So you can go from Smiles, which is the start symbol, to any one of these non-terminal kind of internal symbols, such as chain. Chain has a couple possibilities. It can branch into another chain and a branched atom, or it could go simply to a branched atom, and so on. And down at the bottom, we have things like aromatic organic and aliphatic organic, which map onto terminal symbols. And so the way you build this up, this sort of generative story, is you begin from the start symbol, and you apply these production rules going down the tree in order to create things which are guaranteed to be in the language. So all your syntactic constraints specified in the grammar are here if you have this parse tree. So great, we can take this C1, CCCC1 for benzene and get a parse tree out in our grammar. But we want a sequence. And so fortunately, this is also easy. So we can do a linearization of the parse tree by pre-order traversal, effectively recording in this parse tree which production rules were applied. So starting from the top and going down, and then at each branch we go off into the leftmost branch first, and so on. And so now we have a sequence of production rules as opposed to a sequence of characters. And this is a finite set of productions in the grammar, so we can represent them as one-hot encodings, and put this into actually the exact same neural network model that was used before. So previously, the representation of a molecule was a one-hot encoding of the characters in the smile string. And the big change here is now we're going to use a one-hot encoding of the productions used in the parse tree to produce that smile string. So decoding, we basically run the same process backwards. If you're familiar with the kind of relationship between context-free grammars and non-deterministic pushdown automata, this is going to look super familiar. So we only have to evaluate the decoder network once. So given a value of Z, you can run through the neural network deterministically to get out a sequence of vectors. And these are interpretable as unnormalized log probabilities that are in some sense proportional to what production rule to choose at each step. And the way we're going to use this is like so. So we're going to sample a sequence by sampling a parse tree and build it up top-down. So we start with, we're going to keep track of the current non-terminal on a stack. We initialize the stack with a start symbol, which is Smiles. And at each iteration, we're going to pop the first non-terminal from the top of the stack, recover the unnormalized probability vector, then we're going to mask it to restrict to valid production rules. So we don't want to propose something. So the production rules are all of the form non-terminal to sequence of other terminals or non-terminals, and we just want to restrict that we don't propose anything invalid here. And we're going to sample a production rule and push the non-terminals on the right-hand side onto the top of the stack. So for the next, there we go. So we continue this process basically until the stack ends up empty. So here for chain, there's two possibilities. And so, right, referring to the grammar, chain can go to either chain and branched datum or just to branched datum. So we sample one of these and push to the top of the stack. And we just sort of follow on until eventually everything has reached a terminal and there's no non-terminals left in the stack. And so here, for example, here's our first terminal symbol, C. And so we can record two things as we could run this. We can first record the sequence of terminal symbols we generate, but we can also record the sequence of production rules that we used while running this forward. And kind of the key thing here is at this point, we're done. There's a deterministic map from the sequence to the molecules. And there's a kind of connection here to PCFGs as a generative model for strings or adapter grammars, where basically the fixed grammar defines the production rules, and we have some process which defines the probabilities that are assigned to the production rule at each stage. So some experiments. Before showing you results on the molecules, I think an alternative kind of toy problem we tried this on to test it out was for sort of symbolic regression. So this is a given that you have, say, some x, y data points, can we say, you know, what function is this? Like explicitly, what is the functional form of, what is the expression of this function? And this is also text. Right? This is, you know, is 3 times x times x times x to the 3 halves is text. So here's a simple arithmetic function domain. We have functions of a single variable, a few different operations, a few different primitive functions, a few constants, and some grouping symbols. And so we train this on 100,000 synthetic equations generated from the grammar, and then ask, can we learn from data symbolic form of this particular function? But we're going to do this, we trained this without knowing what the function is. So we could ask this for any function. And the idea is we're just going to learn features out of the grammar, which then are going to be useful for this. Before doing that task, though, let's kind of look. Here's some interpolation between two equations, kind of like the interpolation in the language model before. So the columns here, one of them is the character sequence as the encoding, and the other is the grammar as the encoding. And I think there's the really obvious thing to see is as you interpolate between these, you're guaranteed to have valid equations come out from the grammar VAE, whereas the character VAE, there's places in the latent space that don't actually correspond to things which parse, and so those are marked out in red. But also kind of, we'll see in a moment, this is also in other senses just a more well-behaved latent space. For actually doing the symbolic regression, for saying, well, you know, given a bunch of function points, what form of the expression should we have here? We're using a Bayesian optimization. So this is then given the latent space, we fit a sparse GP to predict the output, and the output here is really we're trying to predict the mean squared error of a function to the points, and so then. This we can use to propose, well, let's go try this, let's go try this, let's go try this, and this will do better or worse, basically depending on how well the surrogate model using the latent space models the domain. And so the grammar VAE is better and faster for this than the character VAE. So looking at the molecules is not a toy problem in comparison. So these, so we trained this on a database from the a zinc database of drug-like molecules on 250,000 drug-like molecules. The grammar itself has 22 non-terminal symbols. The training data, I think, were up to about 120 characters long in the SMILE strings, which was up to about 300 production rules long in the parse trees. So this is a real problem. And so now let's take this and let's kind of look visually at the latent space. And we see that we get something where, like, you do see if you start from a particular molecule and make local changes, you do see kind of things very smoothly. And this is maybe more a pretty picture than anything else, but I think it is a pretty picture. And I think it's like, no, for sure, right? Like you can see like the kind of changes that you might propose back from the first slide, which are chemically motivated, are the kinds of changes that you see in small local movements here for starting from a particular molecule. So now if we try using this for Bayesian optimization, here the target property we're optimizing is for the log p, which is the log of a partition coefficient, which has to do with how, basically it's a good marker for how drug-like a molecule is. And there's a penalization term for how hard it might be to synthesize and for the overall size of the molecule. And so we compare this to the results from using the character variational autoencoder directly. And we find again, using Bayesian optimization, and find that this representation basically allows us to find better molecules that match the target properties that we're looking for. And I'm told, even in addition to the score being higher, the ones in the top row look more like the kinds of molecules that people expect. But that's outside of my expertise. The last thing I guess I would point to as kind of empirical results to show that using this kind of works is the problem for so one is when we sample this, do we actually get out valid samples? So does the decoder, does the generative model produce things which are actually parsed correctly? And so for the expressions, we see the grammar VAE in fact does naturally pretty much always give you things which are valid equations. The character VAE less often. For molecules, it's a dramatic improvement. To be honest, it's twice as often effectively do we see the symbols come out that actually parse. And so the reason it's not 100% here is there's, for the molecules, in addition to being the sort of syntactic constraints, there's also semantic constraints that are outside of the grammar for things about what sort of bonds are permitted and so on. The other thing we can look at is how suitable is this learned representation for the tasks, right? So this is a measure of how well does the sparse GP model fit predicting the property. So one way is looking at the predictive log likelihood, and the other is looking at the mean squared error of the predictions. And in both cases, the grammar VAE gives us a latent space that's more amenable to this. Yeah, great. So a couple challenges, I think. One is not everything is specified by the grammar. So if you think about using this for something like program induction as well, then there's things like is a particular variable actually in scope at this time? That's not a compile error necessarily, depending on your language. That's things that are runtime errors you might not find. And similarly, there's constraints for the SMILES language, which have to do with, say, digits matching across bracing symbols, where you have to have effectively an even number of any particular digit. But that's not something that's specified by the grammar itself. That's a semantic constraint. Thank you.
Thanks. We have time for some questions.
If you're looking at properties that matter in drug discovery, like even basic ones like water solubility, fat solubility, you may notice that they have very similar properties to also what we see in program induction. That is, a tiny change can have a huge effect.
Yeah.
So yes, you have this lovely continuous representation there, but what does it really buy you in terms of predicting properties that matter?
Right.
Sorry if that sounds a little bit too negative, but these kind of tiny changes, they matter a lot to chemists.
Yeah, well, so I mean, I think part of the idea is that you can use this still to drive where to try. So if you're trying to design, well, what large database of molecules should I look at, then the fact that you do have this space maybe lets you help pick out areas of interest. But for sure, I mean, the fact that it's learned in a way which isn't supervised by the particular property means you're really not guaranteed to get anything out there. That's true. So I think this is certainly in comparison to the second talk this morning. There's not this is based off of the structure. So yeah, I think it's good to see actually that this does give you a latent space, which, despite the fact that there may be things like shelves and so on, is still good for this. Yep.
seek-to-seek style models with variational autoencoders for text. There's a reasonably set of papers that all find the same problem. It doesn't really work without adding noise or adding sort of dropout on the resulting sequence, because the RNN-based model is already so good. In particular, there's a recent paper from December from Peter Chen that looks at this problem more in detail. Have you experienced any problem in the VAE bound, in particular the KL term going to 0 and the decoder completely ignoring the latent space? I mean, it can't be the case in yours example because you can interpolate, but more generally, especially in the Baumann paper, they found this as well. And part of the paper deals only with this problem. So can you comment on this issue? Have you experienced it?
Yeah, Matt, I'm going to say we didn't experience it. We took the network architecture as the same one actually used in the previous paper for drug discovery, where it's a 1D convolution as the encoder, and then RNN is the decoder. And to be honest, it worked fine. I don't know if you have more to add there. Okay. Yeah.
Explain by the differences between natural language and the specific data you're working with here. You mentioned that parsers are unique, for example, so I would expect that there's no uncertainty about what string to generate. So could that potentially explain those differences?
Yeah, for the character VAE, for example, then maybe that does explain partially why then it works better. It's just a better behaved language. That's definitely a possibility. Yeah.